Welcome back to Chem 4300. In this video, we're going to continue Chapter 19 on magnetism, angular momentum, and spin. And now we're going to look at the quantum mechanics of adding angular momentum. Now, why do we need to do this? Well, we learned that the electron has an intrinsic spin angular momentum. And when it's orbiting a nucleus, it has orbital angular momentum. So the total angular momentum of a hydrogen atom is going to be the sum of that spin angular momentum vector and the orbital angular momentum vector. So if we want to get that total angular momentum, we have to learn how to add them in quantum mechanics. Now, this might seem like a simple problem, particularly from the classical mechanics point of view. It's just a vector sum of the orbital angular momentum vector and the spin angular momentum vector gives me the total angular momentum vector. And in classical mechanics, we would do it this way. We would just write out into some unit basis. So we would say maybe we're doing it in terms of the Cartesian unit vectors. So we'd have Lx plus Sx equals Jx, Ly plus Sy equals Jy, Lz plus Sc gives us Jz, and we'd have our angular momentum vectors added together. But what's the problem in quantum mechanics? Well, the problem is that we can't simultaneously know all three components of any angular momentum vector. That's because those components do not commute with each other. So we have a problem. We can't add up the components because we only can know one component and the length. We can't know all three components. So we do sort of agree that we're going to decide that Z is the component that we're going to know. So let's say that we can do this addition. We can do the Jz equals Lz plus Sc addition, which tells us that we have a constraint that m sub j, whatever the total angular momentum is, the m sub j value must be equal to m sub L plus m sub S. So that's a constraint that we have, but we're not going to know what the length of the total angular momentum vector is as easily as we do in the classical mechanics case. So what do we know? Well, we do know that the length of these vectors that the total angular momentum can only be as large as these two vectors put end to end here. So in other words, we can't have any arbitrary value for the total length. It has to be constrained by these two limits here. So when the vectors are end to end, the maximum it could be is the length of L plus the length of S, and the minimum it could be is the difference between L and S here. So these are our limits. So we know that the total angular momentum vector has to be between these two limits in quantum mechanics. So if we take this constraint here, we can see that that will translate into this constraint for the angular momentum quantum numbers, which tells us that the angular momentum quantum number, J, has to lie between the absolute value of L minus S and the absolute value of L plus S, but I don't really need the absolute value here because these are always positive. So that's our constraint that we know from that any vectors that get added can get no longer than those two extremes here and here. So let's take a look at how we can apply that. If we have two angular momenta which have quantum numbers of L equals 1 and S equals half, what is the total angular momenta that we can get? Well, the values will range from 1 minus half absolute value to 1 plus half. And that means that we're going to get two possible total angular momenta quantum numbers of J equals half and J equals 3 halves. That means that for each one of those J's, there'll be 2J plus 1 M sub J values. And don't forget that the M sub J value is constrained to be equal to M sub L plus M sub S. So this is what we learn about all the possible outcomes if we try to add angular momentum with these quantum numbers. If I wanted to add angular momentum with which have quantum numbers of L equals 0 and S equals half, what are the possible outcomes? Well, the possible outcomes are absolute value of 0 minus half to 0 plus half. And that only gives me one outcome, J equals 1. Okay, so it's not that difficult to work out what are the possibilities here, but you see it's not what you would expect from classical mechanics. We have to allow for all of these possibilities when we add angular momentum in quantum mechanics. So that means then when we talk about the magnetic dipole moment of the hydrogen atom with this spin and orbital angular momentum, we can still talk about it in terms of the total angular momentum. And what we're going to do is we're going to write down that the total magnetic dipole moment arising from both of those sources is going to be a similar expression to what we saw earlier. Now we're going to write minus Gj, which is something called the Land G factor, which is related to the spin and orbital angular momentum quantum numbers given by this expression here. And that is minus Gj mu b over h bar times the total angular momentum vector. Similarly, we have an expression for the z component of the total magnetic dipole moment based on the total angular momentum z component. And so with this Gj, which is something that you'll be able to derive in one of your exercises, then you can find out what the size of the magnetic dipole moment is, and you can see it's just given by Gj times the Bohr magneton times the quantum number j times j plus 1 under the square root here. So next we come to how do we get the total wave function, which is associated with the total angular momentum of j and m sub j, given that we know the wave function that we start with, which is that we have an L, an m sub L, an S, and m sub S. So how do we make these combinations? So something that's really important is this thing called the Clebsch-Gordan series. So we can express our wave function in two different ways. We can say the total angular momentum wave function, so a wave function associated with j and m sub j, is some linear combination of the wave function associated with L, m sub L, S, and m sub S. We can also flip this around the other way. We can write the wave function as a function in terms of the quantum numbers L, m sub L, S, and m sub S as a linear combination of the wave function written in terms of j and m sub j. Either way, you can do this flip. But what's important is that in this expansion, the coefficients that in this linear combination are coefficients that are called the Clebsch-Gordan coefficients. And these can be looked up in tables, or you can calculate them with various formulas. And one of the things that's important about these is that they will be non-zero if m sub j is not equal to m sub L and m sub S. So let's look at a calculation. Again, I'm going to show you how you can expand a given total angular momentum quantum number j and m sub j in terms of all the possible L and S, m sub L and m sub S wave functions that could combine to give you this function. We could also flip it the other way around, and we'll still use the same Clebsch-Gordan coefficients in that expansion also. So let's take a look at these values. Okay, so one thing I wanted to show you is what one of these tables look like. This is very confusing when you first look at it, and don't worry about that. We'll come back and show you how to do it, but everything in green, in these green boxes here, are the actual Clebsch-Gordan coefficients, and then you just learn how to look them up in this table based on the j value. In this way it's written here, it's the j1 and j2 combined to form capital J, but for our case it's L and S combined to form J, so this would be like L and S combined to form J values, which are then tabulated at the top here. Don't worry about that. This is very confusing, but it's not so bad once you learn how to use it. The numbers inside here represent the coefficients, but you first have to take the square root of them and then apply the negative sign that are shown in these tables. So we'll come back to these in exercises in class. So let's look at how you might construct this linear combination. Let's say that you want a wave function with a total angular momentum of j equals half and mj of minus half. And you know that that's going to be some linear combination of wave functions that have L, m sub L, S, and m sub S. So this is for a p electron in a hydrogen atom. So L is equal to 1 for this p electron. S, of course, for the electron is intrinsically S equal half. So there are two possibilities then for that combination. J equals half and J equals 3 halves. So let's focus on, as we ask here, the J equals half solution. So for J equals half and m sub J we're going to pick m sub j of minus half, but I'll write it generically here for now. That linear combination is given by this expression here. So I've substituted in the L values, L equals 1, S equals half. So that's in this coefficient, L equals 1, S equals half. And since we're calculating the J, total J of half, we put that value here. And what's left in the coefficient is the m sub j, m sub l, and m sub s values. Our summation is over all the possible m sub l and m sub s values. And these magnetic quantum numbers, m sub l, m sub s, have to add up to m sub j. Otherwise, this coefficient will be equal to 0. So expanding this out over all possible values in this sum, m sub s goes from minus half to half, m sub l goes from minus 1 to 1. When you write it all out, you get 6 terms here. Okay, and you can just look at these and verify that that's what you get when you do this expansion here. Now, I've used a notation here to abbreviate the wave function in terms of L and S and m sub L and m sub S. I'm using this notation that we talked about earlier in class, where P of minus 1 is L equals 1 with m sub L of minus 1. Beta corresponds to the electron spin state, so beta of and alpha and beta correspond to m of S of plus or minus half. So looking at this, remember our rule that m sub j has to be equal to m sub l plus m sub s. So you see here m sub j of minus half, here's m sub l of minus 1, m sub s of minus half. These two add together to give minus 3 halves. That's not equal to minus half. So this term is actually going to go away. We'll find that its coefficient is 0. Over here you see 0 and minus 1 add together to give minus half. This one will stay, and we'll have to look this one up. Here we have 1 and minus half add up to get plus half, and that's minus half, so that's not going to stay either. This one will be 0. Here we see minus 1 and half add up to give you minus half, and that's what we have here. This one will stay. Here I have 0 and half add up to give you half. We have minus half over here. That doesn't agree, so that's going to go to 0. And then you see here we have 1 and half give me 3 halves, and here I have minus half. That's not going to agree. So you can see that we can zero out some of these because m sub l plus m sub s has to be equal to minus half. So what we're left with is just these 2 terms. So we have only 2 coefficients that we need to look up in that scary table. And if you look them up, you have to go to the 1 times 1/2 table, and you can find them, and you'll find that there are here 1 over the square root of 3 and minus square root of 2 over 3. And that gives us our expansion on how the total angular momentum, J equals half with m sub j of minus half, is a linear combination of the L, S, m sub L, and m sub S quantum wave functions with those quantum numbers. Okay. If we were writing this out in terms of orbital diagrams, then this is something you learn about in your sort of high school chemistry. Then you would write down that that wave function with the total angular momentum is a linear combination of these wave functions where we've placed these spins in these different states in these particular orbitals. Okay. Now, what do you do if you have 3 or more angular momentum? We've already talked about the nucleus having angular momentum. So what if we have to include the total angular momentum, including the angular momentum of the nucleus? If the nucleus is not I equals 0, then you'd have to combine 3 angular momentum there. So what do? Well, we have different choices on where you want to start. You could add L and S to get a J, which again varies like this. And then you can add to that J the I, and we'll call a new total angular momentum quantum number F, which will range between here. That's one way you could do it. Or you could have done it the other way. You could have added, say, the nuclear and this electron spin angular momenta to get a J, which ranges from I minus S to I plus S, and then combine that J with the orbital angular momentum to get the total angular momentum F. Or you could have likewise added the orbital angular momentum and the nuclear spin angular momentum or nuclear angular momentum to get the total J range, and then add the S to the J's to get the total angular momentum range. So you can do that one of 3 ways. All of them will give you the right answer in the end. So like if I want to take the total angular momentum for states with 3 angular momentum with L equals 1, S equals half, and I equals half, then we can start by, for L equals 1 and S equals half, we find the range of J is half and 3/2. So for the J equals half, we can combine those with the I, and we find we get a range of F equals 0 to 1. And then going back to the 3/2, we can take 3/2, combine it with half here, and we get a total angular momentum of 1 and 2. So what we find is the total angular momentum can be 2, 1, 1, 0. That's the quantum numbers for the total angular momentum. And of course, each one of those is going to have 2f plus 1 values of m sub f. So all told, we're going to have 12 different states here with this combination. And notice that these 2 different total angular momentums of 1 and 1, these are different combinations that we found with one involving J of half, the other involving J of 3/2. So all of this will come out to be the same whether we picked it we did the order the other way around. One of the previous ones that I showed, one of the other options here you could do, and you'll still get the same result here in terms of the total F and the number of states. Okay, so that's it for this video. In the next video, we'll look at taking this all together, look at the fine structure of the atom.